Okay, so let's just begin. I don't think a lot of students are here. Those of you who are not here, you can view it later in the recording that will be uploaded. Okay, so Hanifa is here. Hey, I'm just going to begin now because we're losing time. Okay, so let's just talk about some of the homework problems. I didn't get any list from students that they found anything difficult, but I just thought I picked out 3 problems which I thought were very illuminating to go through. So I'm just going to quickly go through them and talk about how to approach these problems. Okay. So the first one that I picked out is relatively easy, but it reveals a lot about matrix multiplication. So I thought let's just go through them. So the question is, what rows or columns or matrices do you multiply to find all of these different parts, right? So let's say you want to find the second column of the matrix product AB, right? So let's say you have a matrix A. We don't know how many rows it has, how many columns it has, right? This is A, this is B. We know that we can multiply them, right? So maybe this is M by N, and this is N by K perhaps, and then AB is a matrix which would be an M by K matrix, right? And the question is, what columns or rows or matrices do you multiply to find these? The first part says, I want to find the second column of AB, right? So let's say we have the second column of AB. Let's say view AB. So this is AB, right? And so if I start viewing AB as a column matrix, right? Let's say this is the first column, this is the second column, and so on. The question is, what do I need to multiply to get this one? So this one is easy to do if we view this matrix product as producing different columns. If you take linear combinations of different columns of A with respect to B, right? So for example, if I view matrix B as this is B1, this is B2, ... Bn, and if I just take A, let's say if I multiply the matrix A with just the column vector B1, right, then this will produce, and you can check it out, this will produce column 1 of the AB matrix, right? And the reason is that this column is basically the linear combination of the columns of A with this matrix, right? So basically this column is basically A times B1, this is A times B2, and so on. So basically matrix AB can be written as the first column as AB1, second column as AB2, and so on, AB. How many columns will I get? I'll get K columns, so ABK, and so on, right? And that makes sense because B will, of course, have K columns, not N columns, okay, because it's an N by K matrix. So the answer to that problem is that we multiply A with the second column of matrix B, right? So this is a matrix multiplied by a column of B, and which column? The second column. So second column of B, right? So that's how you can find out individual columns of this matrix AB. The second is how do you find the first row of AB? So instead of looking at it in terms of a column matrix, let's view AB as rows, right? So sorry, AB, capital AB. So let's say this was the first row of AB, row 2, and so on. It will have about our M rows, right? And so the question is, how do I get the first row? How do I get this row? And now instead of viewing it as a multiple, so over here in the first one, we were looking at the columns of B and taking the matrix times the whole thing. Here we can instead look at it in terms of the matrix B. You take the whole matrix B, but now we consider the rows of A. So this is A1, A2, and so on. And notice that, so if I take this as, this was an m by n matrix, this was an n by k matrix, right? If I multiply just one row, so if I just take one row, let's say the first row of A, and if I multiply it with the whole matrix B, first notice that the dimensions, so the dimensions of this one is just, this is one row times it has n columns, and this is n times k. So this makes sense that I can just take the one row and multiply it with the whole matrix, because the matrix multiplication is compatible. And the resultant, the result of this matrix row vector times this matrix is going to give me a row vector that is of length, so 1 times k, right? So 1 times k. And this is exactly going to be the first row of AB, because we picked out the first row of column A. So over here you take the whole matrix B, right, and you multiply it with A1 times B, and that gives you the first row of AB. And you can check this out, of course. I'm just claiming this, I have not proved this, but if you want to prove this, you can just go ahead and check it out, that this actually works. Take two matrices and try to multiply one row with the whole matrix. So this, the answer to this problem is that it's, let's call this A1 times B, that is the first row of A times matrix B. Okay. All right. This one and this one, let's look at these. So the parts, two part C is asking the entry in row 3, column 5 of AB. Now they're not talking about just the whole row or the column of AB. They're asking about just a particular entry, right? So if I take this A again and B, so this is part C now. So this is A, this is B, and we're talking about, so they're talking about a particular entry which is in the third row and in the fifth column, right? So that entry is right over here, right? And how do we get this particular entry? We get this particular entry by thinking about it how we used to do matrix multiplication to find individual entries, right? And the way that we used to do that was to take the way we used to do matrix multiplication. So let's say I have 2, 1, 3, 4, and 1, 0, 2, 1. If I'm multiplying these, if I just want to find individual entries, the way we used to do this was take the row and multiply it with the column. So 2 times 1 plus 1 times 2, that gave me 4. That's how I got one entry of this matrix, right? So to get one entry of the matrix, you take one row of the first matrix, let's call it A. So a row of A times a column of B. So this is a dot product, right? So you're taking a row of A times a column of B. Now the question is, this entry will be produced by a row of A times the column of B, but which row of A and which column of B? And the answer to that is, you take, if you think about it in the terms of this one, this was the first entry and the first entry. Now if I want the first row and the first column entry of matrix AB, right? If I want to get this next entry, then I still take this first row and I take the second column, right? So this gives me 2 times 0 plus 1 times 1, which is 1. Now this entry was in the position 1, 2, which is that it was in row 1, it was entry in row 1 and column 2. And the way I got this was to take row 1 of A and multiply it with the column 2 of B, which means to get this entry, which is in row 3 and column 5, I need to take the third row of A and multiply it, take the dot product with the fifth column of B, right? So that's the answer to this one. That is, this is a row A3 dot product, and dot product you can write it like this, or you can write it like A3. Yeah, that's fine. A3, because this is already a row vector and this is a column vector, right? That's the third row times the fifth column. And finally, we have the entry in row 1 and column 1 of CDE, and that's basically just combining these two problems together. I think these two problems together, right? So let's look at it. Row 1, column 1 of CDE. Let's add another page here. So I want row 1, column 1 entry of CDE. Now we have three matrices being multiplied. I don't know of which size. CDE gives me some resultant matrix, and I'm interested in finding out how did I get this entry. Okay, and a neat way of doing that is first to restrict this. Let's say this was CDE. We already know how to find out one entry when we're multiplying two matrices together, right? If we have two matrices being multiplied together, then I know it's just a row times a column. So I can repeat the same process over here, and I think I can say, okay, let's consider this CD as just one matrix for now, right? So CD times E. So this is CD times E, and now the answer is simple. I take row 1 of CD times column 1 of E, and that gives me the entry 1, 1 of CDE, right? And now we're not done yet, because we still need to find how do we got this row 1 of CD, and now at this point we just need to find out, go back to, let's say, part B of the same question, which asked us how do you find the first row of AB. The first row of AB is given by the first row of A times the matrix B. So I can use that information and say, okay, how do I find the first row of CD? That's just given to me by the row 1 of C multiplied by matrix D, and then we have, so this is column 1 of, so this is times column 1 of, and that gives me entry 1, 1 of CDE. Okay. Okay, so that was the first problem. Let's look at the second problem, which I marked out to discuss. So in this problem, you're given two matrices. This is question 10 of, I believe, exercise 2.5, right, from Gilbert Strand's book. And this is the homework problem that I assigned. And I'm going to look at just the second part of this one because that's the interesting part. This is easy to do. You can use the method of finding inverse. So one method that I used to find the inverse of A was to take the following approach. The way you can find an inverse is to augment A with the identity matrix. Then you perform elimination. You perform Gauss-Jordan elimination to get it in reduced row echelon form. And then what you get is you reduce A to the identity matrix, do some row operations so that A becomes the identity matrix, and then the identity matrix will become A inverse, right? And that's easy to do for the first one because it has only, in each row it just has one entry, and so just do a couple of row exchanges and divide by some numbers and it's done. That's all you need to do. But in this one, it won't be as straightforward because each row has two entries, and then that's going to mess up your computations of it. It's not going to be that complicated, but there's another approach that you can take, right? So for B, you can also just take B, augment it with I, do Gauss-Jordan elimination, and get I, B inverse. However, the other approach that you can take is to partition this matrix along after the second column and after the second row, and you get four parts of this matrix, right? So I'm interested in thinking about B as this block matrix, right? So I can look at these different blocks of matrices. This let's call this part B1, let's call this part. I don't need to give it a name because this is just the zero matrix, and I know that this is a 2 by 2 zero matrix. So let's just call it 0. Let's just call it 0, and let's call this P2. So when you look at it in terms of the diagonal matrix, right? So P1, 0, 0, P2, B is just a diagonal matrix, right? And now I'm interested in finding B inverse, which means I want to find B. B inverse is equals to the identity matrix, right? Okay, we can even call B inverse, we can even think about B inverse as a block matrix as well, right? So let's say B inverse is some block matrix. Let's say it has these blocks. So I'm going to partition it into 2 by 2 blocks, same as consistent with this, right? So C1, then it's not right, that's C1, C2, C3, C4. It has all C1s, so C1, C2, C3, C4 are 2 by 2 block matrices. Okay, so this is the 2 by 2. I don't know what the entries are, of course, but there are some block matrices which is partitioned it, right? And we can even view I, the identity matrix, the 4 by 4 identity matrix, as the block matrix itself. We can just call this I, let's call it I2, 0, 0, I sub 2. The reason I'm calling it I sub 2 is because now these are 2 by 2 identity matrix, right? Let me just give you an idea of what I'm talking about. Let me just write the 4 by 4, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. This is the 4 by 4 identity matrix, which I have partitioned into 4 pieces, 2 by 2 blocks, where this is just the 2 by 2 and 2 by 2 identity matrix, and these are just the 2 by 2 zero matrix, right? So that's the approach that I'm taking. And what this tells me is the following. Let's now do B times B inverse is equals to I, 0, 0, I. So we have P1, 0, 0, P2, and C1, C2, C3, C4. Okay, one way to think about this is to, just naively, I can assert that this is a diagonal matrix being multiplied by a dense matrix and giving me a diagonal matrix. Something tells me that this is also going to be a diagonal matrix, right? The inverse, or in other words, you can think of it as the inverse of a diagonal matrix has to be a diagonal matrix, right? So for example, if you had 2, 0, 0, 2, the diagonal is very easy to find. I can just list out it's just the inverse of this number and inverse of this number, multiplicative inverse, and you're done. You can just check it out that this is the inverse, right? You just reciprocate the entries and you have the inverse, right? So something tells me that this is going to be 0. And I can, of course, check that, and I can see. So I can immediately just get rid of C3 and C2, but there's another way to see this if you're not convinced that this is going to be a diagonal block matrix. Because over here, these are just entries, but over here, these are 2 by 2 blocks. So I'm not sure why it should be so. So let's just write out the 4 products, right? So let's multiply this 2 by 2 block with this 2 by 2 block and get this block. So what do I get? So this is B1, let's just do row by column, right? Let's just do row by column. So B1 times C1 plus 0 times C3, that's just 0. So the first entry is B1 times C1. Next up, we have B1 C2, B1 times C2, and 0 times C4. Is just that. This one entry, the third entry is going to be 0 C1 plus B2 C3. And the last entry will be B2 C4 is equals to identity 0, 0 identity. Okay. So I have 4 sort of equations to solve. The first equation is telling me, let me just write down, let's compare the 4 entries, right? The first one is telling me B1 C1 is identity, B1 C2 is 0, B2 C3 is 0, and B2 C4 is identity. So the first equation is just telling me that C1 is the inverse of B1, right? Because if 2 matrices are being multiplied and giving you the identity matrix, C1 is just B1 inverse. And so is the last equation telling me that C4 is just P2 inverse. The middle 2 equations are actually telling me something nicer. Is that if B1 is invertible, if we can get the inverse of B1, I can just multiply it on both sides and get the equation that C2 is simply 0. I get that by multiplying B1 inverse on the left-hand side of both these, of this equation. And this becomes the identity matrix, so it's just C2, and this is any matrix multiplied by the 0 matrix, gives me the 0 matrix. And so does the third equation also tells me that the C3 is 0, right? So when I was trying to find the inverse, I was saying that this is going to be a diagonal block. I was actually right, so this is just 0 and 0. So B inverse looks like this, and C1 is actually B1 inverse, right? So C1 is just B1 inverse, and C4 is just B2 inverse. And that's all you need to do. So basically, if you wanted the inverse of this matrix, just find the inverse of this 2 by 2 block, the inverse of this 2 by 2 block, and just plug it in. And these 2 by 2 inverses are easy to find. You can use this method, or you can use the method you knew in high school, which was 1 upon the determinant times the adjoint. So I'm not going to do the computation. I just wanted to show you how B inverse can easily be seen. So if you have a block matrix that you've written it like this, then you can see that this entry is just going to be B1 inverse. This is 0 block, and B2, right? So you can just find these entries. So I can tell you that B inverse looks like this. The 4 by 4 B inverse matrix looks like this. It contains this. Let me just cut it in 4 blocks. This block is just 0. This block is 0. This block is B1 inverse. This block is B2 inverse. And that's it. Okay. This is problem 18 of exercise 2.6. And this is the last problem. I think this was the last problem in the homework, and this is the last problem that I'm going to discuss. So the first part I think we'd already discussed in one of the Google Meet sessions, but I'm just going to derive this equation for you. The equation is saying that we have two different LDU decompositions of the same matrix A, and all the factors are invertible, which means this matrix is invertible. All of these 6 matrices are invertible, that their inverse exists. With all the then L equals to L1 and D equals to D1 and U equals to U1. This is a fact that they're stating, and we have to basically justify that this is actually true, that L is L1 and D is D1 and U is U1. So how do we do that? First, we start off by finding this equation. So we derive this equation. So I have two different decompositions, L du, and the other one L inverse D, L1 inverse, sorry. Oops, let me just. So this was L1 D1 U1. And the claim is that if these are two different factorizations of the same matrix, then I can combine them together. I can say LDU is equals to A is equals to L1 D1 U1. So I don't need to write A. Let's just say this is the equation. And since all 3 factors were invertible, I can just multiply with L1 inverse on the left-hand side. And this just gives me the identity matrix. So I have L1 inverse LD U equals to D1 U1. And now I can take U on the other side by doing it, by multiplying with U inverse D1 U1. Inverse, this gives me the identity matrix. So I've derived the equation L1 LD D1 U1 UN. This is the equation that we needed to derive, and that's straightforward to do. Now, how does this equation tell me the following facts, that L is L1, D is D1, and U is U1? Okay, and they gave you a hint. The hint is, are the two sides triangular or diagonal? So notice this. The left-hand side, this was a lower triangular matrix, right? So both of these matrices were lower triangular, and this was a diagonal matrix. This was a diagonal matrix, and these two were upper triangular matrices. I'm going to state two facts that you can check out for yourself. And these facts are very important facts that when you multiply the product of lower triangular matrices is lower triangular. And there's a really neat way of seeing this when you look at the linear combinations of the columns of one with respect to the other, and you can immediately see why that must be true. And similarly, the product of upper triangular matrices is also upper triangular, which means on the left-hand side, you can either get a lower triangular matrix or a diagonal matrix, because the diagonal matrix is also lower triangular, right? So the left-hand side is lower triangular, and the right-hand side is upper triangular. And the equation is telling me that both of them have to be equal, which is confusing because let's say I have some lower triangular matrix, right? Everything was 0 over here. This is 0, 0, 0, everything 0 here. I'm taking a 3 by 3 case, but it's generally true. And an upper triangular matrix looks like something like this, right? 0, 0, 0. And how can these two matrices be equal because if this one has something in the upper triangle, this can't match it because 0 can't be equal to a non-zero entry, which means these entries have to be 0. And same case for this one. These entries also have to be 0. So the result is that if these two sides were equal, both of them need to be diagonal matrix. That's the first fact that we found. So L1 LD and D1 U1 U inverse are diagonal matrices, right? Matrices, and they are equal. That's the first fact. That's the first conclusion that we've drawn from this product. What else can I say? Well, look at this. So this is L1 inverse. Now, if I say L1 inverse times L and D, this is a diagonal matrix. That's the first thing. Then D is already diagonal, which means L1 inverse times L is also diagonal, right? So that's something that I know that this has to be, because if these two have something in the lower triangle, then when you multiply it with the diagonal matrix, you will get a lower triangular matrix. So the result of these two has to be a diagonal matrix. And another thing that we know, that when we do LDU decomposition, L and U have ones on the diagonal. So L and U have ones on the diagonal, which means L1 inverse and L1 both have ones on the diagonal. And when you multiply those diagonal entries, then L1 inverse L will also have ones on the diagonal. You can take out some examples that you can check out that this is also true. And so the result is that I get L1 inverse L as a matrix which has ones on the diagonal, and it's also a diagonal matrix, which means it's nothing but the identity matrix. And that takes, now you can multiply both sides. This immediately should tell you that both of these matrices will be equal, because the inverse of one matrix is giving you times the first matrix is 1. I can multiply both sides by L1 and show you that this is L1 times I, and this tells me that this is just L1 times L1 inverse will give me the identity matrix, because this is the matrix being multiplied by its inverse. So the left hand side is identity times L, and the right hand side is L1 times the identity, which gives me the nice fact L equals to L1. Right? So that's the first fact that we have justified for ourselves, that the lower triangular matrix on this side was the same as the lower triangular matrix on this side. At the LDU factorization, at least the lower triangle part is going to be the same if you try to decompose it, right? So it's a unique decomposition. Okay, same argument for the other one. Use the same argument on DU1 times U inverse, and you get, with the same kind of argument, you get U1 U inverse is equals to I, which tells you that U1 is equals to mu. And finally, combining these two together, the original equation told me that L1 inverse LD equals to D1 U1 U inverse. I have established that this is the identity matrix over here, right? And I've established that this is the identity matrix. So this has to be the identity matrix, which means I get identity times D is equals to D1 times the identity, which tells me D is equals to D1. All right, so these were the homework problems that I wanted to discuss, and I think we can start the lecture now. So this is going to be a lecture about some important subspaces, and we're going to now discuss a matrix and its subspaces. Well, not the subspaces of a matrix, but the matrices, the subspaces associated with a matrix, right? So let's talk about a matrix. So the following discussion is going to be about a matrix A, which is M by N, right? So it has M rows and N columns. Okay. So there's two subspaces. We're going to talk about four subspaces, right? Four subspaces. There's two subspaces that we've already discussed, which is the column space of A, which was nothing but the linear combination, the space you get when you take all possible linear combinations of the columns of A. The second subspace was the null space of A, which was again nothing but the solutions of AX equals to, so it was the solutions to AX equals to 0, and that was the space. Today we're going to talk about another space, which is the row space. Okay. And now if you think about it in terms of the same way we defined the column space, that we took all possible linear combinations of the columns, the row space, so in this case we were taking all combinations of the columns of A. In this case we will be taking all linear combinations of the rows of A. So that's the row space that we're going to talk about. And finally we're going to talk about the null space, also called the left null space, but we're going to call it the null space of A transpose. So why did I suddenly bring up null space of A transpose? The reason is that the row space of A, if you transpose this matrix, if this was A was an M by N matrix, if I transpose it, then A transpose is an N by M matrix, with these rows becoming the columns. So the row space of A is actually nothing but the column space of A transpose. And since we've already discussed column space in such a length, why should we change our method of dealing with matrices into row spaces? Let's not look at rows. Let's still look at columns, because that's something that we've been doing for so long. So let's just define this as the column space of A transpose, right? So this is the column space of A transpose, is the null space of A transpose. And now there's a picture that Professor Gilbert Strang likes to draw, and which makes it really illuminating to see how these subspaces are related. But before we draw that picture, let me just answer the question, where do these spaces lie, right? So where are these spaces? So the first subspace, column space of A, each vector, so for example, if I look at the column space, let's take an example. So we take an example, right? So let's take this example. So 1, 2, 2, 3, 4, 5. So this is the matrix A, And now if I want to look at the column space, I'm going to look at all possible linear combinations of the columns, right? So this is the first column, this is the second column, this is the third column. And each column, notice, has two entries, two rows, right? So it has two rows, which means if this was an M equals to 2 and N equals to 3 matrix, then there were three vectors in R2, right? So all of these vectors belong to R2, which means the column space, so the column space of A is going to be a subspace in R2, which means for a 2 by 3 matrix, which means for a general column space, it's going to be in Rm. So each column will have m rows, which means the column space of A will be a subspace of the m-dimensional real space. Okay. What about the null space of A? The null space of A, let's say A, this is a 2 by 3 matrix again. Now, if I want to multiply it, if I want the solutions to Ax equal to 0 solutions to Ax equals to 0, if this is a 2 by 3 matrix, X has to be 3 by 1, which means this X matrix, which is in the null space, is going to have three entries, which means the null space is in Rn, right? Okay. And the same kind of argument you can use for the row space. So the row space now, so the row space of A transpose, row space of A transpose. Well, A transpose is now an n by m matrix, which means each column, so if I transpose this, if I take this matrix and I transpose this, A transpose is 1, 2, 4, and 2, 3, 5. So now you can see that each column has three entries, which means the column space of A transpose will be in R3, which is Rn in our case. So this is a subspace of Rn. So this belongs to Rn, and you can use a similar argument that if I want to multiply it with a vector x, so this is 3, this is 2, and if I want Ax equals to At, x equals 0, then the vector x that I'll multiply it with has to be, if this is 3 by 2, this has to be 2 by 1. So this matrix x1, x2 will have to be, so x is in the space R2, which is basically Rm in this case. So this is where they belong. So this is something interesting, that the column space of A and the null space of A transpose are in the same space, and the null space of A and the row space of A, which is that the null space of A and column space of A transpose, sorry, are in the same space, which is Rn. So let's look at it. Oops, why this page moved here? Okay, that's fine. We'll just add another page here and forget about it for a while. I'll rearrange these pages before I post the notes. Okay, so in the n-dimensional space in Rn, we have the row space, right? And so we have the row space. Okay, let's just make it. So this is the row space. So this is row space, and this is an Rn, right? Row space of A, which is basically column space of A transpose, and this is the null space of A, or null space of A transpose. So the row space of A is in Rn, and the null space of A is also in Rn. So this is how they look. And the other one in Rm, so this was in Rn domain, and in Rm we have two spaces. The first space, this is just a rough sketch. This is not an actual image, it's not an actual visualization, but this is just trying to show you that where these subspaces are. So this is the column space of A, and here we have the null space, slightly nicer, so null space of A transpose, so N A T, This is N A. Okay, this is P of A. Okay, so this is where they are. These two subspaces are in the same space. These two subspaces are in the same space. And so now we can ask a natural question. We were discussing spaces and their spans and bases, and so the question is, we can ask the question: what are the dimensions? What are the dimensions of these four spaces, and how do we find a basis for each of them? Okay. All right. So the first question is really, and both of these questions are related because we know that the dimension is equals to, so the dimension of a space V is equals to the number of basis vectors, right? The number of basis vectors that you want to span that space. And the last class, if you remember, I ended the last class on the notion. We discussed this important fact that the rank of A, which is equals to the number of pivots, is actually the same as the column, the dimension of the column space. So the dimension of column space of A, and let's call that number R. Okay. So here's an important fact that the dimension of this space is dimension of CA. Let's just call it dimension is R. Okay, so that's the first thing. Let's take an example and let's see how you would go about seeing this for a sample matrix, right? So let's take this matrix. Let's say A is equals to 1, 2, 3, 1, 1, 1, 2, 0, 2, and 5, 10, 15, and 2, 3, 4. Okay, so this is a matrix. This is a 3 by 5, 3 rows. You can see that this is a 3 by 5 matrix. And so if I want the column space, so CA, that will be a subspace of R3 because each column has 3 entries. And the null space of A will be in R5. Okay, so let's just first try to figure out the rank, and we can find out what the dimension is, and then we can try to find out the dimensions of the null space as well. Let's do Gaussian elimination. Okay, so we do Gaussian elimination, and the reason I'm doing Gaussian elimination is to use this fact that the rank of A, which is the number of pivots that I get when I do Gaussian elimination, is going to be the same as the dimension of this column space. So let's not waste any time. I know that I need to do R2 minus 2 times R1, and I need to do R3 minus 3 times R1. Okay. So I do that row operation. What do I get? So first row is preserved 1, 1, 2, 5, 2. Second row minus 2 times the first row. So 2 minus 2 times 1 is 0. 1 minus 2 times 1 is minus 1. 0 minus 2 times 2 is minus 4. 10 minus 2 times 5 is 0. And 3 minus 2 times 2 is minus 1. Okay. The third row becomes 3 minus 3 is 0. 1 minus 3 minus 2. 2 minus 6 becomes minus 4. 15 minus 3 times 5 is 15, which is 0, and 4 minus 6 is minus 2. Okay. So this is, I have the first pivot. I also have the second pivot. So I know at least the dimension is going to be 2 of the column space because I already have 2 pivots. And let's just see if we get the third pivot or not. So it seems to me that I'll probably get it because these two entries, these two are different, these two are same. So let's try it out. So R3 minus 2 times R2. Okay. And the resultant matrix is the following. The first row is preserved. second row is 0, minus 1, minus 4 is also preserved. The third row is third row minus twice of the second row. So minus 2 times minus 1, which is minus 2 plus 2, 0. Minus 4 plus 8 gives me 4. 0 minus 0 is 0, and minus 2 plus 2 also gives me 0. So I have indeed the third pivot as well. 3 pivots. So number of pivots is equals to 3. So rank is 3, and the dimension of column space is also 3, right? So I get a 3-dimensional space. So in this case, let me just draw another picture for my example, right? My example, in this case, R was equal to 3. We were in R3. Okay, and now question is, what's the null space? What about the null space of A? Okay, it's going to be a subspace of R5. What about it? How do we check out the null space? What's the dimension of the null space? And the way we find it is very easy. We just look at what would we need to do to find the null space, right? The null space is just the solutions to AX equals to 0. So we just solve this system. And the way to solve this system is just to augment this matrix A with 0. So if I take this, and we'll have to do Gaussian elimination in that one as well. So why don't I just take the Gaussian elimination that I've already done and just augment the 0 matrix, the 0 vector with it, right? Because the 0 vector is not going to change in any of the row operations that I've done so far, okay? So now, once I look at it in this way, that I'm trying to solve AX equals to 0, what do I have? The first thing that I have is I have 3 pivots, R is equal to 3, right? But these 2 variables are going to be free. So if I take this as x1, x2, x3, x4, and x5, these 2 are going to be free. So I have 2 free variables. And if you remember that once you have free variables, the null space is basically, the null space is going to be some, so any vector in the null space is going to be some linear combination of the free variables, right? x4 times some vector plus x5 times some vector. And these are the special solutions that you find, right? And I can do this in this example. It's very straightforward to do. Let's just read off what the 3 rows are telling me. I immediately know that x4 and x5 are free. So let's just find these 2 vectors which will make up our special solution. Okay, so what do we need to do? We just read off the third row. The third row tells me that 4 times x3 is equal to 0, which tells me that x3 is 0. Okay. The second row is telling me that minus x2 minus 4x3 0 times x4 and minus x5 is equal to 0. So I can solve this equation for x2. This tells me that minus 4x3 minus x5. I don't need to write minus 4x3 because I know x3 is 0. Let's just get rid of this. And minus x5, just take it. And x5 is free, so I can just write that x2 is equal to minus x5. So I found x2 in terms of my free variable. And the last equation, the first equation rather, is telling me x1 plus x2 plus 2x3 plus 5x4 plus 2x5 is equal to 0. And let's solve this equation. I can get rid of x3 because that's just 0. No need to write this. And x2 is minus x5, so I have x1 is equals to x1 minus x5 plus 5x4 plus 2x5. So what I've done here is just I've replaced x2 by minus x5, and now I can just see that x1 is, this becomes positive x5, I take it to the other side, it becomes negative x5, so I have minus 5x4 minus x5, okay? So any solution to this null space that has x1, x2, x3, x4, and x5 has the following entries. The first entry is minus 5x4 minus x5. The second entry is just minus x5. Third entry is 0. Fourth entry is a free variable. Fifth entry is a free variable. And if you remember that I can break this down into two vectors, which is, I can say it's x4 times minus 5, 0, 0, 1, 0 plus x5 times minus 1, minus 1, 0, 0, 1. And so let's put x4 here and x5 here, so it's clear to you to see that when I take x4, I get minus 5, 0, 0, and 1 here and 0 here. And when I take x5, notice that what's important here is not x4 and x5. These are just numbers. These are free numbers that you can change. What's important here are these two vectors. These two vectors tell us how I get other vectors in the null space, right? So don't focus on x4 and x5 as much as we need to focus on these two vectors. Okay, so let's just think about what this equation is telling us. This equation is telling us that any vector in my null space, any xn, is some, let's call this v1 and let's call this v2, is some linear combination a times v1 plus b times v2 that is spanned by two vectors. And these are, of course, independent vectors. I can see that these two are not dependent. This entry is 0, but this entry is not 0. That's the easiest way to check that two vectors are independent, at least in the case of two vectors. So I can see that these two are independent vectors. So independent vectors spanning the null space of A, which means these two v1, v2 is a basis. These are independent vectors and they span the whole null space, and this is the basis for the null space of A, right? It has two vectors, and the reason it has two vectors was that there were two free variables. So r equals to, so this was r, and so this was, there were r independent vectors, and there were two, so this became n minus r, right? N minus r. Okay, so this was r equals to 2. So the dimension of the null space, so let's just go back to my picture, the original picture. If the dimension of the column space of A is r, the dimension of the null space of A is, the dimension is n minus r. Okay. All right. And so now we just need to answer these two questions. What about the row space, that is the column space of A transpose, and what about the null space of A transpose? And to do this, you can repeat the same process. What you can do is you can just take A transpose, and the way we found the column space of A and the null space of A, or at least the dimensions of these two, you can find out the dimensions of these two by just doing what we did to the matrix A and repeat that process for A transpose. So that's one way. To figure out the row space, let's just add a page here. So the first idea is that to figure out for row space and the null space of A transpose, we can do Gaussian elimination. Gaussian elimination on A transpose. That's one method. Okay, and we can do that. You can do that at your own free time and figure it out. But I'm going to use two important facts. The first important fact is as follows. The first important fact is that the dimension of row space is the same as the dimension of the column space. And that's a really interesting fact. The interesting fact here is it's saying that the number of columns that are independent here, that there are 3 independent columns. If you take the rows, then there are 3 independent rows, right? So for any matrix, if this, if you know how many independent columns it has, you will know immediately how many independent rows it has. Okay? And one way of seeing that is, notice that once you put this matrix, you were doing row operations on this matrix. When you put it in row echelon form, you can see that these three vectors are, well, the row vectors, right? And these three vectors are independent. They're independent because if you compare this row and this row, this one has 0 in the first entry and this one has 1. And similarly, this one has 0 in both of these first two entries, but the first two have non-zero entries, right? You can, if you can get 0, let's say if you add these two rows, 1 minus 1, you get 0. But when you add them, this entry will become non-zero. So you can never add these two rows to get an entire row of 0, which would have happened if they were dependent rows, right? And we'll do an example so that you can see what's happening. But the point of this discussion is to say that the dimension of this one is just R. And so notice this nice thing that's happening, that if this is R dimensional, this is n minus R dimensional. And if you add the two dimensions, if you add the dimensions of the row space with the null space of A, then that's just R plus n minus R, which is just n, which was that the sum of this dimension and the sum of this dimension gives you the dimension of the space that you were working in originally, which is really nice that it works out that way. And you can immediately think about the same process, that this is exactly what is going on in A and A transpose. What's happening with A transpose in the null space of A is exactly what will happen over here as well. That is, the dimension over here will be m minus r. And the way you can think about it, another way that you can think about it, is if I'm trying to find the null space of A transpose, then let's say if I was trying to find out the null space of A transpose, right? This was A transpose matrix for me. Let me just write this transpose matrix, which was, okay, so this transpose matrix is going to be 23, 1, 1, 1, 2, 0, 2, 5, 10, 15, and 2, 3, 4. So if I'm going to do Gaussian elimination on this, the question I need to ask, how many free variables am I going to get? Well, the number of pivots is going to be equal to the rank of A transpose, which is the same as the dimension of the column space of A transpose, which is the same as the dimension of the row space, right? So the dimension of the row space, I already know that the dimension of the row space is the same as the dimension of column space. That is, let me just write, so this is dimension of row space of A and dimension of column space of A, right? Both of these are same, which means it's going to be equal to 3, which means when I do Gaussian elimination on this, I'll get three pivots, which means I won't get any free variables, which means the number of vectors in the null space is going to be, so this was m, remember, this was m. If I do m minus r in this case, my m is already 3, and my rank of this matrix is already 3, so I get no vector in the null space, right? So this tells me that for this special case, the dimension of the null space is 0, but for a general case, the dimension will be equal to, if there were more free variables, then equals to m minus r. Okay, so in this particular case, it will be m minus, in a general case, it will be m minus r. So that's the dimension of the null space of A transpose. So we've answered the first question, that what's the dimension? And this one is also nice, that if you add these two, you get the dimension m. This total dimension will be m. Okay. All right. It's a lot of information. All right. So the question that we now need to answer is, how do we find a basis for these different subspaces that we have? Okay. So we have 4 subspaces: the column space of A, the null space of A, and the column space of A transpose, and the null space of A transpose. Okay. So for one of these spaces, we've already answered the question D, how to find a basis for that one, and that was the null space of A. And the reason is that as soon as we did Gaussian elimination and we tried to find the special solutions, as soon as we had the special solutions, we had a basis. This was the basis for the null space, right? So the null space of A, so the first is that the basis for null space, basis for null space of A can be given by is given by finding the vectors of special solution, right? The special solution. And this is just by solving Ax equals to 0. Solving this gives you the basis. What about the basis for the column space? The basis for the column space of A, that's given to me. Now notice that when we talk about the basis for the column space, let's say this is a matrix, right? Let's say I'm talking about the column space of A. I have how about we just copy this matrix and let's take it to over here. This was matrix A. Let's call this matrix A. And we transform this matrix into matrix R by, let's call it matrix R, which was the reduced echelon form. When we do Gaussian elimination on this, we got this matrix, right? So let's see if I can grab this matrix. Yeah. And this was the matrix that we got. Oops. Plug it in here. Slightly shorter. And so this was the matrix that we got when we did row reduction or Gaussian elimination on this, right? And so what is this matrix telling us? This matrix is telling us that how many independent columns do you have? Your independent columns, it's equals to the number of, so there are 3 pivots, so the rank is 3 pivots, which means the independent columns are 3 of these columns. Now, so I know that these 3 were my pivot columns. But once you do row reduction on this, row reduction changes these columns, right? The first column of this matrix A was 1, 2, 3, but the first column is 1, 0, 0. These 3 column vectors are different from these 3 column vectors, which means row reduction changes. So the column space of A is not the same as the column space of R, right? And the reason is that row reduction has changed. Gaussian elimination has changed what these vectors were in the first place. But R is still important because R is telling me which columns were the independent columns. And those columns, R tells me that the pivot columns were independent. But I can't take those columns from R. I have to take those corresponding columns from A because I'm looking for the column space of A. So this tells me that a basis for A is going to be the first column, the second column, the third column. For example, if let's just change this for a minute and say this was 4 and this was 0, then this would have told me this matrix R is telling me the first column, second column, and the fourth column. So I would take first, second, and the fourth column, right? So in this case, this was nicer. It was telling me the first 3 columns. So I just take the first 3 columns, which is 1, 2, 3, and then 1, 1, 1, and then 2, 0, 2. So this is the basis for the column space of A. And the dimension works out, right? So the dimension is equals to the number of basis vectors. And we can see that since we said that the dimension is equals to R, the number of basis vectors is also equals to R. So that's how you find the basis for the column space of A. Okay, third problem. Let's add another page. Problem 3 is how do we find a basis for row space, which is how do I find, same question, it is the how do I find a basis for A transpose. The straightforward answer is, of course, how did we find the column space of A? We did row reduction. Row reduction told us which columns to take. I can repeat the same process. I can say I can take A transpose. I can convert it into some R matrix, let's say R2, by doing Gaussian elimination, and then check the pivot columns and then take those columns and get me that would give me the column space of A transpose, right? That's one thing that you can do, of course. But why waste the work that we've already done? Let's look at this matrix again. Let's consider this matrix, okay? Let's take this entire thing. Okay. So let's think about how did we get from here to here. We did row operations, right? Gaussian elimination involves some row operations, which means, what were those row operations? Those row operations, if I go back to, these were the row operations: row 2 minus 2 times R1, row 3 minus 3 times R1, and then finally row 3 minus 2 times R2. So these row operations, they were row 2 minus 2 times R1, row 3 minus 3 times R1, and row 3 minus 2 times R2. These row operations are just adding multiples of two rows, multiple of one row to another, right? Which means it's taking linear combinations, right? Which means it's not really changing the row space, which means the row space of A, so the row space of A is the same as the row space of R. In other words, if I call it the column space of A transpose, is the same as the column space of R transpose. That is because the row operations are just taking linear combinations of the rows, which means the row space is not going to be changed by doing this row operations. Okay, that's the first thing. Now, if the row space is not going to be changed, which means I can just take this matrix and think about what the independent rows are. And over here, it's very easy to see. It's easy to see that the first row and the second row are independent because they're different, and taking a linear combination of them did not give me the third row to be 0. So the third row is also independent, which means these three rows can be taken as a basis. So the non-zero rows of A give me a basis, non-zero rows of R give me a basis for the row space. And I've said non-zero rows, but we didn't really have a 0 row. So let's take an example. Let's take a matrix in which we do get 0 rows, right? So for example, I have 1, 2, 3, 4, 0, 2. And now let me just add these two rows. So 1 plus 4 is 5, 2 plus 0 is 2, 3 plus 2 is 5. I can immediately see that I have taken the third row to be a linear combination of the first row, which means the third row is not independent of the first two. This is going to be, the basis is going to be just these two. And we can see that when we do Gaussian elimination. So first elimination tells me, let's do R2 minus 4 times R1 and R3 minus 5 times R1, right? So when I do that, I get 1, 2, 3. Second row becomes 4 minus 4, 0, 0 minus 8 is minus 8, 2 minus 12 is minus 10. Second one, 5 minus 5 is 0, 2 minus 10 is minus 8, and 5 minus 15 is minus 10. And you can see both of these rows have now become the same. So what I get is now R3 minus R2, and this gives me the matrix, which is 1, 2, 3, 0, -8, -10, and 0, 0, 0. So what has this given me? It's told me that these two rows are non-zero and the third row was dependent, right? Because when I added, notice that row 1 plus row 2 is equals to row 3. And so it can't be a basis. Row 3 can't be part of the basis because it depends on row 1 and row 2. To be in the basis, they need to be independent. So which rows are independent? These rows are independent, right? So that's now I know that these two rows are going to span my row space and they're independent, so they are the basis. So the basis, a basis for the null space of A, the column space of A is given by the non-zero rows of R, that is A after Gaussian elimination. So that's really easy, right? That's a simple process that we can do. Okay. Finally, the question about the last question, number 4, what about the basis for the null space of A transpose? Okay. In the first case, when we were looking at this matrix, let's look at this matrix. This matrix is m by n. So I know the column space of A has dimension equals to 3 and it lies in R3. And I also know that the null space of A transpose lies in the same space, but it has dimension m minus R. This is what we concluded, right? In that picture, we saw that the column space of A and the null space of A transpose are in the same space Rm, and if the dimension of the column space is R, the dimension of the null space is m minus R, where m was the dimension of the space that you are working in. So they were in R3, the dimension was 3 over here, so R is equal to 3, which means 3 minus 3 in this case gives me 0, which means the null space of A transpose. So this is the first example. In this example, the null space is 0 dimension. There is no vector that spans it, which means a basis for the null space of A transpose is just, we don't have a basis because it's just the 0 vector. Sorry. Okay, but what about a case where we do get a null space, right? What if we look at the case over here in which, so let's take this case now. Let's take this entire example that we just did. And for this one, notice that the column space, so this is 3 by 3. This matrix A was 3 by 3. M was equal to 3. N was equal to 3. So in R3, we have the column space of A. We have the column space of A, which has how many pivots did we get in this example? We got 2 pivots. So the dimension, so the dimension of column space of A is R, which is equals to 2, which means the dimension of the null space of A is going to be equal, the null space of A transpose is going to be m minus R, which is 3 minus 2, which is, it's going to be one dimensional. That is, I'll have a basis, at least one vector spanning, not at least, exactly one vector spanning the space, okay? And the question is, how do we find it, right? So far we noticed that for the basis for, let's look at these questions that we've answered. So the basis for null space of A is given by finding the vectors of special solution. So we just did Gaussian elimination, and we used the same Gaussian elimination for the basis of column space. And we even were able to use the same Gaussian elimination process to find the basis for the row space, which means it would be really nice if we are able to do just the same process, make use of just the same Gaussian elimination and try to find the null space of A transpose as well, because then it just tells me all I need to do is do Gaussian elimination and I can combine that to get the dimension of the null space. Okay, so it's there, null space of A transpose, sorry, the basis of the null space of A transpose. I'm sorry, I said a lot of things, and let me just rephrase what I was saying. I was saying that I want to see the basis for the null space of A transpose, and I want to see it using Gaussian elimination, not on A transpose because that's something that we haven't done yet, but I want to do it on A and see how I can use that to find the null space. So the first thing that we need to understand is what is the null space of A transpose. The null space of A transpose is solving ATY equals to 0, right? Or rather just by y. ATX is equals to 0. So solutions of A transpose X. And one way of finding that is of course the same way that you find how did we find AX equals to 0. Found the special solutions for this, that gave me the basis. If you transpose A and find the special solutions, you will get a basis for the null space. There's no question about it. You can use the same method. And I just don't want to do the same process again on the transpose, right? I want to avoid doing that. So the other thing that I want to do is I want to see it, let's transpose this. Let's transpose both these sides. And notice that what I get is A transpose transpose. If you remember, A B transpose was the same as B transpose A transpose. So this side is going to give me X transpose, A transpose, whole transpose. The order changes and then you get a transpose on both of them. And the right hand side is just 0 transpose, right? So this is telling me that xt, sum xt times the transpose of the transpose is A is equals to the transpose 0 vector, right? Okay, what does that really mean? Let's look at it in terms of this example. Let's take this matrix and let's see what the equation is telling me. So first it was telling us, so I can now look at it in terms of the equation that we were solving was ATX0. We were solving ATX0, but so if I take A transpose, so A transpose X equals to 0 gives me this equation 1, 2, 3, and this becomes 4, 5. So the rows becomes the column and the column becomes the rows. The first column is 1 to 3, the second column is 4 0 2, the third column is 5 to 5. And we were solving the equation x1, x2, x3 gives me the 0 vector 0, 0, 0. We transposed both sides and we got this equation. So what is xt A equals to 0 going to look like, right? A equals to 0 transpose. So this is A. X transpose is going to look like this row vector because this X is a column vector. So this is x1, x2, x3. Some row times this matrix giving me the 0 vector. Okay, that's what we have to find. We have to find some row times this matrix to give me the 0 row. And I'm going to leave this right here and do a process that we already have done before, right? So I'm going to now take you back to this elimination and I'm going to ask you, what was the elimination matrix that took us from this matrix to this matrix, right? So what was that matrix? Let's try to find that matrix. So the first one was R2 minus 4R1. So on this matrix, we performed these steps. The first one was 1, 2, 3, 4, 0, 2, and 5 to 5. We first did E to 1, that is elimination of this second entry by the first entry, and we did what the process that we did was R2 minus 2 times R1. So this matrix, I can make this elimination matrix 1, 0, 0, preserve the first row, preserve the third row, and for the second row do minus 2 times the first row, 1 times the second row, and then just 0. The next step that we did was R3 minus 3 times R1, and the matrix for that is preserve the first row, preserve the second row, for the third row minus 3, 0, 1, and lastly we did R3 minus 2 times R1, and that was 1, 0, 0, preserve the first row, preserve the second row, 0, minus 2, 1. This was E31 and E32, okay? And you might be confused at this point is why am I going back to this process, but it's going to turn out really nicely. So I want you to have some faith in me and just follow what's happening. So this was the Gaussian elimination process, and the idea is when you were doing Gaussian elimination, keep track of this elimination matrices, right? And so what happens? Okay, so let's combine these three matrices into one single matrix, right? So let's multiply E21 and E31 together. I get 1, 0, 0, and preserve the second row minus 2, 1, 0, minus 3, 0, 1. So the first two matrices just multiply very easily together. 1, 0, 0, 0, 1, 0, 0, minus 2, 1. Okay, let's find, and A was of course here, right here. 1, 2, 3, 4, 0, 2, 5 to 5. Okay. All right, let's combine these two. Just the last thing that I need to do here, and then we'll have the answer. So 1, 2, 3, 4, 0, 2, 5 to 5. That's A. And if I combine these two together, preserve the first row 1, 0, 0. I'm just multiplying these two matrices. This was E32. Second row as it is, minus 2, 1, 0. Third row we get 0, minus 2 times this row. So this is minus 3, minus 3 plus 4, which is 0. So which is minus 3 plus 4 is 1, and minus 2 plus 0 is minus 2, and then minus 2 and 1. So this is the matrix E. Okay, why did I do this? That's the big question here. Why did I build this elimination matrix out of the steps that I did? Okay, let's see what we have on the right hand side, E times A. When we did this elimination process, notice that what we ended up with was this nice matrix 1, 2, 3. So on the right hand side, when you eliminate entries 1, 2, 3, and what was it? 0, minus 8, minus 10, and 0, 0, 0. So 0, minus 8, minus 10, and 0, 0, 0. Okay. And now I just want you to focus on this third row. This third row is 0, 0, 0. And at the start of today's lecture, I showed you how you can find this row by taking one row of this. So if I want to jog your memory, let me go all the way back to the first problem that we were doing. And the question was, how do you get a particular row of a matrix product? And the answer was, if you want the first row, just take the first row of the first matrix and multiply it with the entire matrix, right? And that's how you can get all these rows. So, which means I can see that this row, the third row, can be built 0, 0, 0, can be built by taking this matrix as it is, A matrix, just take this A matrix and multiply it with the third row, of E, which is 1 minus 2, 1. And you can check this, right? So 1 minus 2, 1 will give you 1 times this, minus 8. Wait, what? Did I make some mistake? So 1 times this, minus 2, that doesn't really work out. So I get 1 minus 8 plus 5. I think I've made a mistake in building this E matrix, so let me just find that mistake. So I had 1, 0, 0, 0, minus 2, 1, 0, 0, minus 2 is minus 4. Okay, so this should have been minus 7, I think. Minus 2 is 4, minus 3 is 1, that's fine. And minus 2, fine. Where did I make a mistake? Did I multiply these two correctly? 1, 0, 0, minus 2, 1, 0, and minus 3, fine, minus 3, 0, that's fine, minus 3, 0, 1, 0, 0, that's fine, also fine, 0, 4, minus 3 is 1, and 0, minus 2, plus 0, minus 2, and that's fine. Okay. Why isn't this working out then? So row times column, 1 times 1, minus 8 plus 5, that should give me 0. Okay, let's just see if I copied the elimination steps correctly or not. This was, oh, my bad. This was R3 minus 5 times. Okay, let me just correct this. So this was 5. This must be 5 then. And so we get a 5 here. And now we can have minus 2 is 4, minus 5 is minus 1. So this is minus 1. And now I have minus 1. And what will this give me? 0, minus 2, 1. Is this, do we have the right result now? So 0, minus 2, 4, 4 minus 5, minus 1. Let's see if we get the right result now. Okay, let me just correct my computation mistakes. Let's see if we find what the issue is. So R2 minus 4 times R1. Okay, I have completely botched this process because I think oh, so it's 4 minus 5. What did I copy? What process was I really doing? Never mind, I've done it all wrong. This was 4, 5, and minus 1. Oh dear. 4, 5, and minus 1. So this should be 4 and minus 1. Let's see. Yay. So I have minus 4. This is 4 minus 5. So this is 4. Okay. And minus plus 4. 4 minus 5 is minus 1. And what is this entry? Minus 1. Okay. Minus 1, minus 1, and minus 1. So this is the third row. Let's hope one last time that this is correct. Okay. So what do I get? Minus 1 times 1 is minus 1. Minus 4 plus 5 gives me 0. Minus 2. Okay. We have it finally. So minus 2 and plus 2 is 0, and minus 3 minus 2. Okay. This works now. This is fine. Apologies for that computational error. Okay. So let's see what we've got in here. The reason I picked out this row, okay, let's go back to the conversation that we were trying to have, which was we have this matrix A multiplying with A, giving me this reduced matrix which has a 0 row. So I just focus on the 0 row and take it out, right? And what the 0 row is telling me that there is one row that you can multiply with this matrix to get a 0 row. And that's really what I was looking for when I was looking for the null space of A. I wanted a row that when you multiply with A gives you the 0 row. and that should work. This minus 1, minus 1, 1, when you multiply it with this, gives you the 0 row. So I can even check this, that this is the solution to the null space of A transpose, right? So my claim is that this is A transpose times this vector, if I transpose this now, right, will give me the 0 vector. And we can check this. We can check this by transposing this. So this is 1, 2, 3, 4, 0, 2, 5, 2, 5. And if I now do, so this is A transpose, this is X, the X that I wanted was minus 1, minus 1, 1. And you can check that the solution is 0. So 1 times minus 1, minus 1, minus 4, minus 5, that's 0. This gives me 0, and multiplying this row gives me 0. So a solution is minus 1, minus 1, 1, which means I can make a basis. So the basis for the null space of A transpose is given by minus 1, minus 1, 1. Right? And it has only one vector because we had decided that it was going to be one dimensional, right? So dimension of null space is going to be one dimensional, and we found it by finding the solution, right? So the idea was, let me just recap what happened. The idea was you take A and you do Gaussian elimination on A, but you keep track of these elimination matrices, and then you take out the 0 rows that you're getting. In this case, I got only one 0 row because I knew that my row null space of A transpose will be one dimensional. So I saw that I can take this row and I can get this row by taking this row multiplied with this matrix. So this gives me a solution. If I had more rows, for example, let's add another row to this matrix, right? So 1, 4, 5, 1, 2, 3, blah, blah, blah. And if I have, let's say for the sake of argument, let's add another row to it. Let's add 5, what's another row? So another row would be 1, 2, 3. If you do Gaussian elimination on this, then you will get two rows which are 0. This one is 0 and this one is 0. And the reason is this row is the same as this row. But you will get some non-zero entries here, and actually, since this is the same matrix, you will get 1, 2, 3, and 0, minus 8, minus 10. So 1, 2, 3, 0, minus 8, minus 10 once you complete the Gaussian elimination process. And so the question is, now you have two rows. And how do you find the null space, the vectors corresponding the rows? You just find this elimination matrix that you were doing with, and you take the two rows that gave you these two rows, right? And that will give you the null space. So these two will be in the basis for null space. Okay. I'm going to recap all of this. I know we're a little bit over time, but I'm going to recap what I just said. So we have the following. Let's try to make a straighter line this time. So I have the following. I have the column space of A. I have the null space of A. And A is, in this case, the dimension of, A is an M by N matrix. Okay. So the column space is in Rm. The null space is in Rn. Then I have the row space of A, which is actually the column space of A transpose, which is in Rn, and the null space of A transpose, which is in Rm. Okay. Okay, so what is the dimension of this column space? It's equal to the rank. Let's call it R. The dimension in this case is then going to be also equal to rank, which is R. Then immediately we have the dimension for the null space of A transpose, which is rank, which is N M minus R. And in this case, the dimension is going to be N minus R. Okay. How do we find a basis? The basis is given by the pivot columns. So you identify. So let me just write two important things. The first thing is that the number of pivots we are assuming is R, and we are taking A to R by Gaussian elimination. Okay, so identify pivot columns in R, then the corresponding columns of A give the basis. Okay, that's how you find the basis for the column space of A. What about the basis for the null space? This you just solve AX equals to 0 using Rx equals to 0. So you already have it in reduced form, you solve it, you find the special solution, then you have the basis. Okay, what about the row space? The basis for the row space was also easy. We saw that we can take the rows, we take the non-zero rows of the reduced matrix R, and just transpose them so they are column vectors. For a basis you want column vectors. And finally, what about this? This was the last case that we did. We take out the rows of the elimination matrix E, and that gives us 0 rows in R. Okay, let me just go through all of them. So the null space of A transpose, this was matrix A, this was matrix R. R had a 0 row in the third row, and the third row of E was in the basis for null space of A transpose. So that's what I mean when I say that the rows of the elimination matrix E that gives us 0 rows in R. Similarly, this is something that we've already done, non-zero rows of the reduced matrix, right? So these two non-zero rows will give me the basis for C of A transpose, that is the row space, is just going to be 1, 2, 3, and 0, minus 8, 10. That's the basis for the row space. And the basis for the column space and the null space of A is something that we've looked at the start. Let's just give you that as well. So basis for the null space was immediately when you solved, where is that? Basis for the null space of A is given by finding the vectors of the special solution that we already did, right? Where is it? This is the one, right? This was the basis for the null space. And finally, the basis for the column space you got by identifying the pivot columns and then taking those pivot columns. This was the basis for the, there we go. Okay, and that's it.